Okay, great. So, what we're going to talk about is what is a mineral, and then, like I said, how that plays in with atoms, all the way up to rocks, all the way up to field environments. So, as an example, here's a picture from the Sierra Nevada of some granodiorites. Here's a picture of some rocks, the minerals that make up those rocks. Would you guys mind turning off the front light switch, please? And that will make the pictures less washed out. Thank you. So this is a picture, a photograph of granite. And in granite, we know that there are minerals like quartz and amphibole and feldspar, potassium feldspar. Okay, sometimes when you know the composition of the feldspar, the potassium feldspar, you might call it orthoclase. And then these are the atomic structures of each of those minerals. So quartz and potassium feldspar, we'll learn down the road, are framework silicates. And so we have this organization of the atoms. And amphibole, as we'll learn in the next few days, is a chain silicate, and it's actually a double chain silicate, and so you see here two chains, 1, 2, that are connected together. Okay? So all of these have a role to play with one another. So we're going to zoom in and zoom out. And this picture here, or this slide here, sort of encapsulates our whole semester. Okay? We're going to learn a bit about the atomic properties. We're going to learn a bit about minerals, and you guys have already started doing that by reviewing the minerals that you looked at in Lab 2. We're going to do some review and then in-depth investigation of rocks. That will start tomorrow. And all of this is so that we can be adept and able to conduct ourselves in the field. Okay? And that's sort of the goal for this class, is to be able to use our knowledge of rocks and minerals to understand what we're seeing in the field. Okay? And we might go back to the lab and do more with some of those rocks and minerals. And this is a picture of Chad. He graduated last spring, so this past May. Some of you might know him. He did some research to try and investigate the emplacement, the lava flow emplacement of some lavas in the Lassen region, and we'll go and look at his field area on our field trip. So he took some rocks and he looked at them under a microscope and then zoomed in and looked at the rocks under a higher magnification microscope. So you guys will learn how to use the microscopes next semester. And then he took it to a high power microscope where he could look at almost to the micron scale. And then what we wanted to do, or what he wanted to do, was try and reproduce some of these textures of the minerals to try and figure out how fast those minerals crystallize. And by doing that, he was able to hypothesize how fast the lava cooled as it was flowing. Okay? So this is a 100,000-year-old rock, so nobody was around to measure how fast this lava flow was in place. So the best way to estimate it is with some models that he used, and then also with some experiments where he was able to, this is a furnace where he put the sample inside the furnace, heated it up to the temperature that it would have erupted at, and then cooled it at different rates. So 5 degrees C per hour is the result of this experiment. And so he was able to reproduce this level of crystallinity in order to estimate how fast the cooling would have happened. So that's one way that we can use minerals to understand the rocks in the field. Okay? And Evan and Nate, I think you guys know them, they're working in the same field area, and they're working on basalts, and those basalts are, of course, made of olivine, pyroxene, and plagioclase. And what they're looking at and presenting at a meeting this fall, they're looking at using the minerals to try and estimate the pressure and temperature at which the source magma was sitting in the mantle. Okay? And so there are some models that they can use. We analyzed the composition of the olivine and the plagioclase, and used the models to predict what pressure and temperature these rocks were at when they were solid before they melted and erupted. Okay? So by understanding some in-depth detail about rocks and minerals, we can start to make some statements about what happened in the field. Okay? How did these rocks erupt? How fast were the lavas flowing? Those kinds of questions are questions that students are working on now. But you guys have to get the basics so that you can get to points where you might be asking these kinds of questions and doing the experiments and the research to be able to participate in projects like this. But I wanted to give you sort of a big picture outcome. This is not just a rite of passage. You must memorize all of these minerals because I said so. There are actually some applications that have important ramifications. Okay? All right, so let's start in the middle with the mineral. We're not going to go to the atoms quite yet. We're not going to go to the rocks quite yet. Let's go to the mineral. So today, what I'm going to ask you to do, and actually throughout the semester, is I'm going to ask you to write some things down in your notes before I tell you the right answer. So, what I suggest is you pull out another implement of writing, okay? And you write it in, you write your ideas that I asked you in black, and then you correct that in blue, and or whatever. And what that does is later, when you're going back through your notes, you'll be able to say, oh, the stuff in black is the stuff I already knew. I barely even need to study that, because I already knew it. I might need to just refresh my brain, but I don't need to learn it. The stuff in blue, or whatever the other color is the stuff that I really need to pay more attention to, because that's the stuff I didn't know off the top of my head. Okay? It's also a really good way to build your confidence. Okay? These are the things I already know. These are the things that I need to learn. All right? So what I would like you to do is tell me, what is the definition of a mineral? How would a mineralogist define this? Okay? So go ahead and work on this for about a minute, and then I'll tell you what's next. Does anybody need another color? I have some other implements of writing here. If you get stuck or done, maybe confer with somebody else who looks like they're stuck or done, and decide what color you want to write that in, if you choose to write down what they suggest. Okay, so now's the time, if you would like to chat with your neighbor, now's a good time to do that. Like, you're going to have to get a swivel seat, huh? Okay. So, this is a multifaceted response. Okay, there are multiple responses to what is the definition of a mineral. So, I'd like to hear one component of that response. So, who's got one idea of the definition of a mineral?
You just want one part of the definition?
Yeah, one part. Scott, you want to go first?
It has a specific crystalline structure.
Okay, perfect. said, right? Now I got distracted, sorry. Okay. Anyone else? Yeah, Trish?
Solid.
Solid, yep, good. Who else? Yeah, Dennis?
I have that positive one or more elements.
Okay, so composed,
Not from biological.
what was that?
Not from biological processes.
Okay.
Organic, yeah.
Whole inorganic.
Does that fit what you're saying, Robert, too? Inorganic?
Maybe.
Okay, how about we'll put both of them up and then we can decide. Inorganic, or you said not from,
Biological.
Yeah, maybe the exception if it's called, I
like, biological process? Or
It's not from life.
not from life? Do you want to just,
Life doesn't produce something like.
okay, not from life. Okay, and then what were you just saying, Dennis?
well, with the exception of like bitters, coal, or maybe,
Okay.
maybe even chert, because that comes from life, doesn't it?
All right, what else? What's not up here that's on your page?
It makes up rocks.
Okay? What else?
Specific chemical composition.
Okay?
Physical property.
What was the one, I heard it but didn't really hear it.
Physical properties.
Okay? Anything else? Okay, what do we want to edit? What do you like or don't like up here? Besides the agenda.
You know what the specific chemical composition composed of one or more elements are basically together. they're
Okay.
Together.
Okay, are they the same thing? Which do we like better if they're not the same thing? Jason, you like specific chemical composition better? Okay, so can we omit then composed of one or more elements or keep it? I'm seeing a few head nods omit. Okay, good?
Abiogenic is what I meant.
What is it?
Abiogenic.
Okay,
Not inorganic.
Okay.
Biogenic.
what's that?
Oh, I thought it was like abiotic.
Abiotic. And you guys are in terms that I'm not clear on. Okay. What else? Which ones do we want to keep? Which ones do we want to not keep? Or do we want to keep them all?
I like inorganic.
You like inorganic? Okay. Do we like this whole thing? Not from life except coal and chert. Why not?
Well, because you put an exception in there.
Okay. What does everybody else not like about it who mentioned they don't like it? I saw heads shaking no.
Well, organic from life, right?
Okay, yeah.
So, inorganic, except not from life.
Okay,
I don't know, I don't know what to think about that, because I've always heard that it says a naturally occurring inorganic solid.
Okay.
Inorganic, but then, you hear the books talk about the exception of like coal,
okay.
or in chert is from a biological process.
Okay, what do we think about coal and chert?
I think you've got to keep them as exceptions.
Are they minerals?
They're not minerals.
They're not minerals.
Are they minerals? What's chert?
Church of rock.
What's coal? A bunch of compressed leaves. Yeah, picture gasoline for my car. Or I guess heat, yeah. Okay, yeah, it is also not a mineral. So we don't need this exception.
We don't.
Okay, because they're not minerals. Because remember, we're defining the mineral. Okay.
So once coal becomes diamond, then it's an inorganic.
That's interesting.
I'm not sure that coal necessarily becomes diamond, but diamond is a mineral, coal is not. Okay, So coal doesn't have a specific atomic structure, okay, or crystal structure, as you guys said. I'm going to change that to atomic. Okay. So we have 1 rule, 2 rules, 3 rules, 4 rules, and 5 rules. In order to be a mineral, does it have to make up a rock?
No.
It would be prouder, right? I mean, I belong to a rock, right? But you can have a mineral, like you guys looked at minerals in lab yesterday. They were real minerals, but they weren't in rocks. Okay, so we don't have to have them in rocks. Okay, and then what about physical properties? Does it have to have physical properties?
No, it doesn't all matter.
Okay, so does that help define it as a mineral? No. Okay, so we don't need it to have that. Okay, Dennis, you were going to ask a
I was
question?
gonna say, you know, when I wrote it, I had specific atomic crystalline structure.
Okay, that's fine.
So-
Yeah, remember the crystal form, like we talked about yesterday, is based on the atomic arrangement. So we can.
So we don't need the crystal.
That's right. Yeah. Okay. All right. So you guys nailed it with a little bit of extras on the side, but that's okay. All right. So these are the 5 rules, 5 requirements for something to be a mineral. So if a material is presented to you and you're not sure if it's a mineral, then you can test it with these 5 requirements. Does it fit all 5 of these? If any one of these is missing, then it can't be a mineral.
I've got a question.
Sure.
Okay, I've seen like some crystals that are made in China that
Yeah.
are man-made,
Right,
which, you know, they have a specific chemical formula. They
right.
have structure, they have
Yeah.
all the things that minerals have, but they're man-made. Is that,
So does it satisfy all 5 of our rules?
it does not.
Okay, so it ain't a mineral. It can be, they may call it a mineral, but it's not a naturally occurring mineral. So it's a man-made,
But it may be a.
it's a
mineral
man-made
also.
crystal. It
Yeah.
shouldn't be technically called a mineral. Okay. So like synthetic diamonds, they use synthetic diamonds a lot in the industry for polishing and for saw blades and stuff.
Yeah.
Those are not minerals. They're not.
But they have the same structure.
That's right.
as mineral.
That's right. Yep. Or jewelry sometimes.
They're not.
Well, zircon is a real mineral, but there are man-made zircon things, materials. Okay, so you guys nailed it. That's awesome. So the first thing is, I mean, on my list, the order doesn't matter, okay, but I'm just going to go through each of these. So the inorganic is probably the easiest way for our number 4, the easiest way to call it. And it basically means there's no carbon, hydrogen molecule in the mineral. Oops, there's an X there over a picture of coal. Okay, so coal is not, and that's the perfect example. It needs to have an orderly internal structure, so the atomic structure is organized. What happens if you melt a mineral and those bonds break? Is it still a mineral? It's not the same thing anymore, exactly. It's solid. Does that picture convey solid? Drew was solid in his knowledge. And has a definite chemical composition, as you all are participating in for tomorrow, right? There's the deadline for us. We have that minerals formula quiz tomorrow. All right, so here they all are, all 5 of them. Pretty much the same, worded slightly differently than our list over there, but the same 5 components.
So ice is a mineral
Why?
because it contains all of those.
Because it contains all of those. Do you guys believe that? He said ice is a mineral. Does it follow all of those? 2-0.
I don't know, is it naturally occurring if it's warmed in my freezer?
Yeah, I don't know. That's a good question. Ice on the ground, how about that? If you poured water into a tray. I guess I don't know the answer to that. Stop trying to stump me. It's too easy. Okay. So all 5 of these need to be satisfied. Okay? All right. So now we know what is required to be a mineral. And some of those requirements are related to the arrangement of the atoms, or the presence of the atoms. What are some ways, just think about this for a second and jot down in your notes. What are some ways that atoms influence minerals? What are some ways atoms influence minerals?
What are we gonna decide?
Okay, hang on, we're not sharing quite yet. Just jotting down in our notes for a second a few ideas. Unless, did you have a question about my question? Okay, you're giving answers, huh? Okay. Yeah, I'm just giving everybody a chance to think. If you get stuck, go ahead and confer with another person near you. Share ideas. There's a whole bunch of right answers. Okay, even if you're not done, why don't you go ahead and chat with somebody next to you and compare ideas. Okay, what are some ideas that folks came up with? Tons of right answers here. Go ahead, Trisha.
Bonds.
Bonds. Tell me about bonds.
Different bonds, for instance, affect how the crystal will, like how the crystals form.
Okay, so if the atoms are bonding together, then that's going to, like you said, control how the crystals form.
Yes.
Okay, great.
And different atoms prefer different bonds or different bonds.
Okay. And so how is that going to impact a mineral?
It could impact it through the strength of it,
The strength of what?
the mineral.
Okay, and what do we call the strength of the mineral? Hardness. Yeah, you got it. You got it. You're like, I don't want to answer that question. Dennis.
It contributes to the luster, cleavage, and density.
Okay, tell me one of those. How?
One of those.
Yeah. How does it contribute to one of those?
Well, to the specific cleavage planes,
Okay.
because of the crystalline structure, it's going to determine how that mineral might break.
Okay, how is it going to determine?
Because of how the atomic structure is
the alignment of the atomic structure. How else can we phrase this? You're right on the right path. I just need some more details. Yeah, Robert?
Geon, the atomic ionic arrangement usually expresses itself in its crystal structure.
Okay, and how is that controlling the cleavage? Anybody jump in here?
Stronger, weaker.
Yeah, really?
The weak spots, yeah.
Oh, okay, sorry. You guys both said it at the same
Yeah.
time.
It's stronger
He said
than weak bonds.
Okay, so there are strong and weak bonds. Okay, now finish that. Really?
And the weakness is where it breaks along.
There we go. Okay, so let's put this all together and say that the cleavage planes are going to occur where the weak bonds break as opposed to where the strong bonds are sticking together. Okay, does that make sense? I'm not sure I said that very well. Who else could say it better? Anybody could say it better. Who's willing to? How did you write it down so that it made sense to you? You just wrote down what I said even though it didn't make sense? Who wrote it down better than what I said? Who wrote it down differently than what I said? Come on. Among us, we can make it.
Alright. Can we have like ionic bonds are gonna be are gonna be weaker than the covalent bonds, and the hydrogen bonds are gonna be
Yep.
weaker than those? And
Right. So we have different strength bonds, absolutely. And somebody was going to take a shot at it. Was that
I was
Katie?
gonna say cleavage planes occur where bonds are weakest.
Ah! Does that make sense? Okay, good. Sometimes you guys can phrase it better than I can, so I'm happy to have you guys rephrase stuff. Plus, when you put it on in your own words, then it's going to make more sense to you. Okay? If you're just writing down the nonsense that I say, in my head, he just wrote down nonsense. Does that have two E's or just one? Okay, great. So, good deal. So we're going to keep moving forward. We're diving deeper into the chemistry. What do you remember about an atom? Quick, draw one and label it. Go for it. What components are we labeling on our atom? Say again?
Everything I know about an atom is the opposite of what people generally know about gases.
I don't know how to respond to that.
It's not that structured.
How about somebody who's actually drawn it? What have you labeled? Yeah, Mario?
On the electronic cloud.
Okay. What kind of cloud? Cloud of.
Yeah, electronic.
There you go. You got it. You got it. We're just fine tuning it. Okay. So there's an electron cloud. Okay. That's what's supposed to be represented by these gold wild things. Okay. What's in the middle? Protons and neutrons that make up the. There we go. Okay. So you guys remember a lot. Ooh, bad colors. You guys remember. Oops, sorry. A lot about an atom. Even though you took chemistry now, last semester, 3 years ago. Okay? Alright, those are the main components for sure. So an atom is made up of electrons, neutrons, and protons, and it's the smallest unit of an element. Okay? So then an element is a collection of atoms, but more specifically, all of these atoms have the same number of protons. Oops. And the same atomic number. And there's the part about the protons, same number of protons. So the example I give there is that carbon always has 6 protons. Scott Scallon is thinking of an exemption, an exception.
Can something not have isotopes?
Yes. What's an isotope?
It's a different amount of neutrons and
Ah, okay, so can carbon still be, it'll still have the same number of protons, but the isotopes of carbon will have,
carbon 10, carbon 15.
right, and so why are those different numbers?
There's different
Neutrons, that's right, yeah. So we're gonna keep the same number of protons, but the number of neutrons can change for an isotope.
So an element can have isotopes in it.
Yes, absolutely, right. You're just like jumping like 10 minutes ahead. Were you gonna say something, Joe?
Pretty much that.
Okay, great. All right, so an element can be made of a single type of atom or multiple atoms, which would be molecules. And this is the level of detail of chemistry that I think we're gonna need for like the next 6 or 8 weeks. But we need this. Okay, for our electrons, protons, and neutrons, what types of details can we add? What distinguishes them?
An electron has a negative charge.
Okay, so the charge is one aspect that we can think about. What's another aspect?
Their
Size?
protons and neutrons affect mass, electrons really don't.
Okay, and the mass. That's exactly the charge, the mass, and then the location is something that we already talked about. The electrons are in the electronic cloud, and the protons and neutrons are in the nucleus. Okay? So just as a review, sorry about the darkness here. The electrons have a negative charge, like Marilyn said, so therefore they're attracted to protons. Okay, we need to remember that because when we start talking about bonds, we need to think about opposites attract, so on and so forth. Their location is orbiting the nucleus, and their mass, as John pointed out, is essentially none. Okay, negligible. Whereas, oh wow, totally invisible text. It's super helpful. Protons, what's the charge? Positive. Okay, and what's the weight in AMU? 1. Yeah, 1 AMU. And the protons dictate the atomic number. So, for instance, carbon atomic number is 6, and that means that there are 6 protons. Okay?
That's interesting. Like the proton is only MU and the electron is almost equal, but the electron is an equal charge.
Right, so equal charge, but different mass. Yeah. Okay. And then the neutron is sort of the opposite of that, right? It has no charge, but it has 1 AMU. Okay? So in the nucleus, the protons and neutrons that are in the nucleus combine to form the atomic mass of the element, and neutrons and protons have about 1 AMU. Okay. Everybody good with this? I'm hoping this is a review for everybody, but just to make sure we're all on the same playing field, I felt like we needed to go through it. Okay, so the atomic mass is the neutron and the proton. 1 AMU is dictated, not by me. I did not get consulted in this, okay? But somebody decided, some group of people decided that 1 AMU is 1/12 of the mass of carbon, okay? So that's what it is, all right? Let's just get beyond our frustration, get beyond what we would prefer, and go with that. Okay, so carbon is here on the periodic table. I don't know if you guys noticed, there's a periodic table over here. It'll stay up for the whole semester. And when you get your books, there's one in the back of the book as well. Okay. All right, so we mentioned isotopes. And so for any carbon isotopes, how many protons will it have?
6.
Okay, easy, right? Or is it 12? You guys can't be tricked. All right, how many neutrons will a carbon isotope have? How many? Pick a number.
6.
Who said 7? Good. Who said 5? Good, Dennis. He's waffling. Yeah, you're all right. Okay.
Because it's both.
That's exactly. Yeah, it can be either. Okay, so the isotope is going to have a different number of neutrons. All right, that's the beauty of the isotope. It's flexible. All right, but in order for it to stay the same element, we have to keep the same number of protons. As soon as a proton wanders away, then we change everything. All right. Oops, that's backwards. Let's keep going. So the atomic weight is the weighted average of all the isotopes, the natural isotopes of the element. Okay, so carbon, it says up here, is 12.011. Okay, so you take the weighted average. Do you know what it means by the weighted average? So if there's a lot of the heavy isotope and only a little bit of the light isotope, then the heavy isotope is going to have a larger proportion. Okay? All right, ions. How many kinds of ions are there that we care about?
2.
Yep, 2. Does anybody remember what they are? Cation. Somebody else? Anion. Okay. So an atom with a positive or negative charge is an ion, and it's just because the protons and electron charges don't balance. And so an ion that's positive is cation, and the negative ion is anion. Okay? Why would it have a charge? Because the number of neutrons changed? Oh, the electrons. Okay. Okay. So when the number of electrons doesn't equal the number of protons, then we have an ion. Why do we care about cations and anions?
Bonds.
Say again?
Bonds.
Bonds. What about bonds?
Bonds.
They form bond. They can bond together because they have this attraction. Okay, a positive and a negative will attract. Okay, so that's exactly right. So let's do a quick run through of the periodic table. We know that it's a collection of elements, and we know that elements are made up of a collection of atoms. The periodic table is organized in columns, so the vertical features are columns, and those are called groups for the periodic table, because we have to have different names for things. Okay? And the rows that go across here, left to right, those are called periods. Each period has a different electron arrangement. Okay, do you guys remember the 2s, the 2p, the different orbitals? Okay, so notice that the orbitals become more complex. All right, they also become, because they're more complex, there's more of these orbitals, and so they actually make the elements get bigger from the top to the bottom. Okay, that we care about. We care about the size of the elements. Okay, the reason for it is the orbital complexity, or numbers of orbitals. Okay. The groups, or the columns on the periodic table, have increasing number of protons from left to right across any row, across any period. And so that means that the atomic weight is increasing from left to right as well. Okay. So, in general, the groups, or the elements that are on the left side of the table have a few extra electrons, and the groups, or the elements that are on the right side of any of these rows, have need a few extra electrons. Yeah. Okay, so that's going to set us up for bonds being able to form. Oh, and let me just give you some names because you'll see them in the readings. The first group is called the alkalis. Okay, those elements are the alkalis. The second group, or the second column, are the alkaline earths. These are the transitions. The second to the last group is the halogens, and the last group, or the last column, are the inert or the noble gases, and those are really stable. Okay, so they're not going to have a lot of substitutions. All right, but we do get substitutions, and one of the mineral formulas that you're learning for tomorrow is nepheline, and you'll notice that nepheline's formula has the sodium and the potassium are in these parentheses. Why are they in parentheses? Yeah, Sam?
Can you use either one?
You could use either one. Well, I can't use, but nepheline can. Right. Okay, so they substitute for one another. All right? So, that sometimes, like in olivine, that one of you memorized inappropriately, too early. It's not inappropriate, but just earlier than necessary. We know that we have iron and magnesium substitute in olivine. Just like in nepheline, we have sodium and potassium that can substitute. Okay, so an appropriate formula for nepheline would be 1 sodium and 1 aluminum and 1 SiO4. Or it could be 1 potassium and 1 aluminum and 1 SiO4. Or it could be half of a sodium and half of a potassium and 1 of the rest. Okay, as long as whatever adds up inside the parentheses adds up to 1, we're good to go. Okay? Now, notice where sodium and potassium are on the periodic table. They're right adjacent to each other. What's different about sodium and potassium?
Weight. That's, atomic weight.
The number of protons.
The number of protons. Okay? What else is different? The atomic mass. What else is different?
Well, they're S&P orbitals.
Yes, so what is the S&P orbital arrangement is different. How are those different? Yes, one's bigger than the other, because remember that as we move down the rows, down the periods, then we get bigger elements. Okay, so potassium's a little bit bigger than sodium, right? But not that much bigger. It's not like cesium is trying to fit into a site that sodium would occupy. Okay, so that substitution makes sense. It's an okay substitution. The site that in the atomic structure where that sodium fits can also accommodate potassium. Okay? That's the beauty of the periodic table, is we can look and see how are things going to fit. Okay? All right, I think I'm going to stop there. But before we do, any questions?
Does that go for any time I see a mineral formula with a comma?
Anytime they're in parentheses.
In parentheses with a comma.
Yes. So, and let me say one more thing about that.
Like half the
Do you
time.
remember all of these?
I don't, because I
Okay.
put it in my bag right away.
Yeah, no, that's okay.
But like half the time. it's-
Okay, so look at this. Now we have magnesium and iron in the parentheses. Either one of those can fit, but they need to add up to 2. So we can have 1 Mg, 1 Fe, SiO4. Or we can have Fe, 2 SiO4. Or whatever arrangement fits. So that this component has 2. In the nepheline example, there was no number after the parentheses, so that just implies 1.
Can we have fractions as well?
Yep, so we could have Mg 0.75, Fe 1.25, SiO4. Is that what you were going for? Okay. Doesn't that add up? 0.75 and 1.25? Okay. You're just messing with me. Okay, so this is, we still have our two of the MGs and MDs. Okay, so that works, and then we haven't changed our SI on 4.
You can't put 3 foot, so add them. Well, I guess it's short.
No, but you could scale up. All right? Okay, great. Then I will see you guys tomorrow. Not with this memorized.